Swayam Prabha. Digital India. Educated India.
Hello, welcome to Introduction to Composites. Today is the last day of the ongoing week, which is the 6th week of this course. Yesterday we had initiated the discussion on how to predict transverse modulus of unidirectional composites, and using the assumption that the stress in composite, matrix and fiber are the same, as well as the assumption that the extension in the composite is nothing but the sum of extensions in matrix and fibers. We had developed a relation for transverse modulus, and that relation for transverse modulus was 1 over Et, where Et is the transverse modulus of composite. It equals volume fraction of fiber divided by its modulus plus volume fraction of matrix divided by its modulus. So, this is our first model. Now, let us look at this graph. So, in this graph, what I am going to plot on the y axis is the modulus of the material of the whole composite, and on the x axis I am going to have volume fraction. So, volume fraction could vary anywhere from 0 to 1, that is 0 to 100%, and we assume while making this graph that the fiber modulus is 10 times that of matrix modulus, because you have to make some assumption. So, EF is 10 times that of EM, and once we have that, we can make this plot. So, this is the relation for ET. For EL, what is the relation? For EL, relation is EF VM VF plus EM VM. Okay. And of course, we assume that Vm equals 1 minus Vf. We do not assume that there is any air or something like that. Okay. So, first we will develop a line for EL. So, when fiber volume, so this is 2, 4, 6, 8, 10. Okay. When fiber volume fraction is 0, what is the value of EL over EM? 1. When fiber volume, so first we are going to develop a line for EL. First, this is first thing we are going to do. We are going to develop a line for EL. When fiber volume fraction is 0, volume fraction of matrix is 1. This number will be 1, right. So, this is 2, 4, 6, 8, 10. So, this curve for EL will start from here, and as volume fraction keeps on increasing, this is a linear relation, right. As volume fraction of fiber keeps on increasing, this number will keep on increasing as a straight line. And what is the maximum possible value of EL? When volume fraction of fiber is 1, this term will be 0, and this is Vf is 1. So, EL will be same as EF, and EC over EM will become 10, because this is what we have assumed, right. So, this will be a straight line. So, this is the relation for EL, okay, or rather EL over EM. Now, we use this relation to compute the behavior of Et over Em. Okay. we use this relation to compute ET over EM, and if we do all the mathematics, the graph looks something like this. So, it starts and ends at the same location. Why does it start at the same location? Suppose at 0% volume fraction, this term goes to 0, this is 1. So, 1 over EM is equal to 1 over ET, so it starts from 1, and at 10%, at 100% volume fraction, it ends at 10, because we have assumed that EF over EM is 10. Okay, so this is how. So, this is the expression for ET over EM. Now, these both lines are theoretical lines based on our models which we have developed. This model, when we look at experimental data for EL, so what does experiment tell? It agrees very well for EL. So, if we take samples and pull them in longitudinal direction and we find experimentally the values of EL, you will see a lot of values. It will be along this line, which means that actual value of the longitudinal modulus of a composite is pretty close to our predicted value. So, we can reliably use the equation for EL, but for does not agree very well, does not agree with ET. So, if you look at the data for ET, it looks something like this. It starts at 0 and ends at 10, but in general the actual value of ET, transverse modulus, comes out to be significantly higher than the calculated value of ET. This is important to understand, which means our model for ET is not a good model to predict this value. So, our model for ET is not good enough. So, we do not want to use this expression for computing ET. So, what do we do? Before I explain how do we compute the value of ET, we should try to understand what is the reason why this model does not predict the value of ET reliably enough. There are a couple of factors. So, let us look at some of these factors. Reality. So, when we were developing this expression for ET, we had assumed this kind of a configuration. We made this picture, or we made this picture, we made this picture and we made this picture, and we said that there are layers of fiber and matrix, layer of fiber and layer of matrix, layer of fiber and layer of matrix, right. But in reality they are not layers, there are fibers continuously dispersed throughout the medium, and throughout the medium you also have matrix continuous. The fibers are still in the transverse direction, the orientation is not different, but they are continuously dispersed. So, we do not have layers, so we cannot have this block kind of a system which we do. Now, so first thing is fibers are continuously dispersed in the medium. In T direction. Now, what does that mean? What that means is that at every cross section, see earlier we had assumed, what did we assume? That stress in the matrix and stress in the fiber and stress in the composite is same. But if in the same layer you have fiber and the matrix, then you cannot make this assumption, right. Then what that means is some stress is being shared by the fiber and some stress is being shared by the composite and by the matrix. So, stress is actually shared, it is not same because it is not layer by layer model. So, that is the one thing. Second thing is, when we apply load on the fiber or on the system, fiber expands and the matrix expands in the transverse direction, right. And when they are expanding in the transverse direction, there will also be Poisson's contraction in the other direction. See, when you pull something, it becomes longer, but it also becomes slimmer. Okay. So, because of this Poisson's effect, matrix will become slimmer and also fiber will become slimmer, and but both these things will not be same because the material properties of matrix and these things are different. So, fibers are continuous. So, what this means is load is shared between fiber and matrix. So, we cannot state that sigma f is equal to sigma m is equal to sigma c. There is one thing we have said. The second thing is Poisson contraction due to transverse load is not same in fiber and matrix. It is not the same. So, what does that mean? Typically, so one part of the material will expand less, other phase will expand more or contract more, and so on and so forth. So, what this means is that fiber and matrix, because they are not in the layer, they interact very tightly with each other. And as a consequence, because of both these effects, fibers constrain expansion of the matrix. They constrain expansion of the matrix, and if this constraint happens, then what will happen? The extension in the length of the composite will be less. So, this causes lesser delta C. If delta C is less, this will lead to higher ET. For the same stress, there will be less extension, less strain, which means higher ET. And that is the physical reason why a lot of this experimental data shows these are experimental point, is higher than the predicted value of ET. Okay. So, to find the actual more reliable estimate of ET, there are several ways to solve this problem, but at least in context of this course we will not go to those methods, but rather I am going to share with you one result which gives reasonable good prediction of ET directly. So, what we can do is, so that method is known as, it is a formula. So, we will use this formula known as Halpin-Tsai relation for ET. So, this gives reasonable prediction. It gives reasonable prediction for ET. What does this say? That if you want to compute ET, you can compute it using this relation. ET over EM equals 1 plus zeta eta Vf divided by this term, and this is a parameter. So, neta is a parameter and it can be computed by using this relation. And then you will wonder what is zeta. So, zeta, it depends. If you have circular fibers which have circular cross section, then it is equal to 2. If the fiber is having a rectangular cross section, let us say the cross section is like this A and this is B, and the fibers are oriented in such a way that the load is in the length of A direction, then this is equal to, then zeta equals to A over B. But most of the times we use fibers with circular cross section, so we do not have to worry too much about this. So, we can use this, and with these, so zeta, you can say most of the fibers are circular in cross section, unless you go to some fancy wires, metallic wires and things like that, where there may be non-circular cross sections. So, you can use this too. From this you can compute neta. From neta you plug it in this relation and you can find ET, which is the transverse modulus, and this relation gives you a fairly good estimate of transverse modulus of composites, unidirectional composites, and that is pretty much what I wanted to cover for today. Next week we will continue this discussion, and we will also develop relations for other materials, other properties of the system like transverse strength, Poisson's ratio, shear modulus and things like that. So, the discussion for this week is complete, and I look forward to seeing all of you next week on Monday. Have a great weekend. Thank you.